In a previous video, I talked about processor interrupts and the difference between the non-maskable interrupt and the normal interrupt request line here on pin 4 of the 6502 processor. And the way it works right now is when I press this button, the interrupt request line is pulled low, and that causes the processor to finish executing whatever instruction it's on and then immediately jump to the interrupt handler. Right now, that interrupt handler just increments a counter and then exits and returns from the interrupt. And then the rest of the program is just a loop that prints that counter to the screen here. The problem is that when I press the button, the interrupt handler runs and increments the counter so quickly that as soon as it increments it, I'm still pressing the button. So it goes right back into the interrupt handler, increments it again. That's why when I press the button, the counter is incremented a bunch of times. It's so fast that no matter how quickly I press the button, even if that button's pressed for just the shortest split second, the interrupt handler will still run hundreds of times. So in this video, I'm going to look at how to use the 6522 versatile interface adapter chip here to provide a little bit more control over how interrupts are generated and handled. And remember, if you want to follow along with this video or any of the other videos in this series on the basic 6502 computer, head over to my website at eater.net/6502 for more information and kits that include everything that you need to follow along. Now, so far, the way we've used this 6522 versatile interface adapter here is really just for input and output on the 16 data pins that it provides down here. And mostly, we've really just used it for output to the LCD module. And remember, the way that it works, if we look at the pinout for it, there are essentially two 8-bit ports. So there's port A, 0 through 7, port B, 0 through 7. And those 16 bits we can control programmatically. We can either read or write to them from our program. And the way that we've been outputting data to those ports is just writing to these registers that are in the 6522. So register 0 and register 1 are for the output or input register for B and A. And so those correspond to these the two 8-bit ports here that we've been connecting to. We can also set the data direction for each bit. So there's a data direction register for B and A on registers 2 and 3. And we've been setting those in order to control whether these bits are either input or output. And then our address decode logic is set up here so that these registers, 0 through F, actually appear to the CPU at addresses 6000 through 600F in hex. So if we go up to the top of our program here, we can actually see we've got that defined. If we go all the way up here, we've got port B at 6000, we've got port A at 6001, we've got the data direction register for port B at 6002, data direction register for port A at 6003. That corresponds to these first 4 registers here in the datasheet for the 6522. And then here, for example, you can see we're actually storing something or writing out to the DDR-B. We're setting the data direction register B. Here we're setting the data direction register A. So this is how we output data to those registers. So that's these first 4 registers, but there are a bunch of other registers you can see here to perform other functions on the 6522 processor. And that includes a couple registers here for interrupts. And that's because we can use the 6522 interface chip to generate various types of interrupts and interface with the 6502 processor in order to make it easy to sort of handle those interrupts. And to understand how that works, we can actually flip over to page 25 here of the 6522 datasheet. And there's a description of interrupt operation. And it talks about the interrupt flag register, it talks about the interrupt enable register, IER, and it talks about the IRQ pin and how all of those work for interrupts. And you can kind of read through this for maybe a more complete understanding of how this works. But basically, the way it works is we've got this IRQ pin, and that IRQ pin is really it's pin 21 on the 6522 chip. And the 6522, when it generates an interrupt, it'll use that pin to signal that interrupt to the 6502 processor. So basically what we want to do is really just connect that pin up to the interrupt pin of the processor. So we connect pin 21 here, the IRQ pin of the 6522 adapter, to pin 4 there of the processor, which is the IRQ or interrupt request line. So this will allow the 6522 to signal the 6502 processor when there's an interrupt, and that'll cause our interrupt handler code to run. But then we'll have to figure out what caused that interrupt. So if we look back at the interrupt operation for the 6522, it also talks about these other flags registers and so forth. And so if we look here, there's an interrupt flag register that we can read. It's at address D, which in our case would be 600D. We can read this flag register, and it will tell us what caused the interrupt. So So when the 6522, however it's configured, some kind of thing that creates an interrupt happens, it'll signal an interrupt here. Well, then the processor can then read this interrupt flag register to see what caused the interrupt. And you can see there's a bunch of different types of things that could cause the interrupt. There's some timers that we could configure. There's shift register functionality. If you're reading serial data in here, there's an interrupt that will trigger when the shift register fills up and there's more data to read. So there's a bunch of different functionality that's supported. You can read through the whole 6522 datasheet to learn more about that stuff. But there are also these 4 bits for CA1, CA2, CB1, and CB2. And those actually correspond directly to pins on the 6522. So we've been looking at this port A, port B, these 16 bits here, but there's also CB1, CB2, CA1, and CA2, which are just 4 more pins that we could use. And in the case of these 4 pins, we can actually have interrupts fire when the data level changes on those pins. So for example, if we wanted an interrupt when we push this button, we could hook the button up to the CA1 pin, which is this pin right here. And so when we push this button, CA1 will, in this case, let's see, it'll go low. And there's a way for us to configure the 6522 so that when the CA1 pin goes low, then we'll trigger an interrupt. And the CA1 bit in the interrupt flag register will be set to tell us that's what triggered the interrupt. So that's how this flags register works, is when you get an interrupt, you read this flag register and you can figure out what caused the interrupt just by looking at which bit is set. But there's a couple other things we need to do in order to set this up. So the interrupt flag register will tell us what caused the interrupt, but we actually need to enable that interrupt first. And there's another register for that, which is the interrupt enable register, which is very similar. So it's got the same interrupts. Well, if you ignore that first bit for the moment, it's got the timer interrupts, the CB1, CB2, the shift register, CA1, CA2. So this interrupt enable register looks very similar to the interrupt flag register. It's just that the way this works is we write to this register to tell it that we want to enable the particular interrupt. So if we want to receive this CA1 interrupt, so we want an interrupt when this pin transitions, then we have to enable that by writing into this interrupt enable register. And the way that works is this first bit is a set or clear bit. So if we want to enable the interrupt or set the interrupt, then we'd have that bit set to a 1. And then we'd also set the interrupt that we want to enable to a 1. So the CA1, we'd set that to a 1. So we'd set those 2 bits to a 1 and write to this interrupt enable register, and that will enable the interrupt for the CA1 pin. And then I guess if we wanted to disable it, then we'd set this to a 0 and then set this to a 1 and write it again, and that would disable it. So let's actually go ahead and do that in the code here, because we'll want to initialize that at the top of our program here. So let me actually create a couple aliases here for those additional registers that we're going to be talking to. So we have the interrupt flags register, and that's at 600D, right? Because a register D here is the interrupt flag register. And then the interrupt enable register is 600E, right? So that's 600E is the interrupt enable register. And then at the top of the program here, we want to initialize the interrupt enable register to enable interrupts from that CA1 pin. So load a value of 82 hex and store that into the interrupt enable register. So we look at the interrupt enable register. So 82, so the 8 will be for this nibble here. So the 8 will set the set bit. So that'll be set. And then the 2 will set the second bit here, CA1. So 8.2 will set the interrupt enable for the CA1 pin. So once this interrupt is enabled, then we should start receiving interrupts when we push this button. That'll cause the processor to generate an interrupt. Well, there is actually one other configuration thing that we can do, because CA1, what that says is that's going to activate an interrupt on a CA1 active edge. But it doesn't say whether that active edge is a transition from low to high or a transition from high to low. Both of those would be considered edges of a waveform or signal. And it doesn't actually say which one. And in our case, we want it to be a negative going edge, because right now this CA1 pin is tied high through this resistor. It's tied to 5 volts. And when we push the button, it'll connect it to ground. So pushing the button will transition it low. But it turns out we can in fact configure that, because there's this other register here, the peripheral control register, that gives us the ability to control that. So if we look at the definition here for the peripheral control register, you can see it's got CB2 control, CB1 control, CA2 control, and CA1 control. And these are used for setting up the mode or the operation mode for those CA1, CA2, CB1, CB2 things that we would receive interrupts for. And in our case, we're hooked up to CA1, so there's one bit that allows us to control it. And if we look at how that's defined, CA1 interrupt control, if we set that bit to a 0, we get a negative active edge. If we set it to a 1, then it's a positive active edge. And it just says, which type of edge is generating the interrupt. In our case, we want a negative active edge. So we want to make sure that this bit 0 in the peripheral control register is set to a 0 to ensure that we're getting the interrupt at the right time when we push the button, not when we release the button. And the way this works, works the same for CA1 and CB2, or excuse me, for CA1 and CB1. For CA2 and CB2, it works a little bit differently. You can do the same thing. So you can see both of these have a little bit more options to them because you've got 3 bits. But you can kind of do the same thing because there's a negative active edge if you set them all to 0. There's a positive active edge if you set 0, 1, 0. There's also this sort of independent version, which you can sort of read the note. It works very similarly, but the way you clear the interrupt is a little bit different. You can also use it if you're using this handshake option, which is described in the data sheet a little bit more detail. Or you can also use those extra pins as just output pins. So you could set the pin to low, or you could set the pin to high, and it would just work as an output pin. So you get a little bit more flexibility with 2 of those pins. But in our case, we're just interested in having an interrupt trigger when we push the button. So we want to set our CA1 control line or control bit to 0. And the rest of these we don't really care about. So I'll just write a 0 to the whole peripheral control register and leave it at that. So the peripheral control register is address C. So go ahead and define that. Peripheral control register is C. And we'll just write a 0 to it. And it may actually default to that. This may not be necessary, but it seems like a good practice just to make sure it's set the way we expect it to be. Okay, so we've set the interrupt enable register here so that we're receiving interrupts when the CA1 line transitions. And we've set the peripheral control register so that happens when it transitions to a low state. So at this point, once we update the program, of course, when we push the button, that should cause the processor to generate an interrupt. And we'll have our interrupt handler that increments a counter, just like we've been doing before. But now what we need to do is the thing that we couldn't do before, which is clear the interrupt. So before the problem was, when I push this button, the interrupt line would go low because it was directly connected to it. But then that interrupt would keep firing because as soon as the interrupt incremented the counter, it would return from the interrupt routine and then say, oh, wait, there's still an interrupt because the button is still pushed. And it would go back and increment the counter again and again and again because essentially the interrupt was triggered anytime the button was depressed, not just at the moment where it transitioned low. So that's the thing that we're getting out of this, right? Because we have that ability to detect that low going edge and only fire the interrupt then. But then what happens is once it goes low, the 6522 will transition the interrupt request line low to signal there's an interrupt. The processor will then go into the interrupt handler routine, but the processor needs to tell the 6522, okay, I've handled that interrupt. You can release the interrupt request line and let me kind of get on with business. And so to do that, there's a description here that tells you how to clear each interrupt. So in our case, the CA1 active edge interrupt is set when that active edge transition happens. And then it says it's cleared by reading or writing to the output register A. So the idea is that if this pin, the CA1 pin transitions, the way you clear that interrupt is actually by reading port A, which is these first 8 bits here. And I think the idea there is that if you had 8 bits of data going into port A, you might have them sort of ORed together and hooked into this pin here, so that if any of them changed, you would have some way of detecting that. So you could have like a bunch of buttons. You could have them all sort of ORed together and sent into this PA1 pin here. But then each individual button would go into a different bit of port A. And then when you press any of the buttons, it would trigger the interrupt. But then when you read port A, you could figure out, okay, which button was pressed. So I think that's why it's designed this way. But in any event, the thing you do to clear the interrupt is reading port A. So if we go back down to our interrupt handler routine here, this is what's going to happen when the interrupt happens. We increment our counter, and then if it rolled over, we increment the next byte of the counter, and then we exit the interrupt routine. So the change we need to make here is we need to clear the interrupt before we exit the interrupt routine. So we can do that right here. And really, we could do a load A, port A, and that'll do a read of port A, and reading port A is the thing that will clear the interrupt. I don't necessarily want to do a load A, because if we did that, we would have to push A onto the stack and then pull A off the stack before we return from the interrupt, because we can't just overwrite the A register inside the interrupt because we don't know when the interrupt's going to get called. So we could do something like this. Another thing you can do is use the bit command, which does a bit test of port A. So what that'll do is it'll do a read of port A, and then it'll do a comparison and set some of the processor flags. When an interrupt is called and when you return from an interrupt, the processor will automatically push the flags onto the register and pull them off the register. So by doing this, we are overwriting some of the processor flags, but that's okay because they'll be restored when we return from the interrupt. So this just is a little bit of a shortcut. So we don't have to worry about overwriting the A register. But this will do a read of port A, and reading port A is the thing that's going to clear our interrupt. So those are really all the changes we need to make. So I'll go ahead and save this, run the assembler, and we'll get the EEPROM into the programmer here, and go ahead and program it. There we go, and let's give it a try. Put the EEPROM back in, power up and reset. So there we are at 0, and so now when I push the button, it should cause an interrupt, but then the interrupt should be cleared, and we shouldn't get subsequent interrupts because there should only be one negative going edge. And there we go, we got one interrupt, 2, 3. Well, we got a few, but I think that we got a few because the switch is bouncing, right? Because there's no debouncing circuit in here. So when I push the switch, the contacts might bounce, and each little bounce is going to cause a negative going edge, and it's going to count every one of them. So if I'm careful, I can have it count by ones, but every now and then I get a few extra counts in there. And there's actually, a few solutions to that. One solution would be, proper debouncing hardware, which I've talked about in previous videos. You can check out the video where I do that with a 555 timer. Another possible way to do this is actually do it sort of in software, where we could add a delay before we reset the interrupt to allow that bouncing to sort of settle down. So what I'm thinking in terms of just a sort of quick and dirty way of doing some software debouncing would be to add a delay here before we reset the interrupt. So the interrupt is triggered, we increment our counter, and the problem is that we reset the interrupt so that then if the switch continues to bounce, we're going to get further interrupts. But if we put a delay in here, then what would happen is we increment our counter. The interrupt is still sort of asserted. We're still in the interrupt handler routine. If we sit around for a little bit of a delay, then any switch bouncing would presumably happen during that delay period. Then we reset the interrupt and return from the interrupt handler. Well, hopefully in that case, we won't get that bouncing. So to create a delay, what I can do is just write a loop. So essentially, I'll just load a big value into the X register, and then basically just count down to 0. So decrement the X register, and then do a branch if not equal, which will test the previous decrement against 0. And if it's not 0, then we can stay in a loop. So I can branch to a delay, and then delay could be right here. So here we go. So we start with FF, so 255. We decrement. If we're not at 0, then we jump back up to delay, we decrement again, and we just keep sitting in this loop until we decrement X all the way to 0, and then we exit the loop. So that'll cause a little bit of a delay. If we want a longer delay, we can put another loop outside of this loop. So we can load Y with a large value as well. And then when we're sort of done with this inner loop, then we can decrement Y. And as long as that's not 0, we can jump back up to this delay. And this will essentially give us 2 loops counting from 0 to 255. And that should create a pretty decent delay that should absorb any of the switch bouncing. In fact, if anything, it might be a bit long, but we can see how it behaves. Yeah, the obvious downside to this, of course, is that we have this big delay in our interrupt handler. So anytime we handle an interrupt, we have this giant delay in here. So that's not necessarily ideal. So I'm just kind of showing you this as an example. It might be better to handle the switch bouncing in hardware or handle it in a more sophisticated way in software or something like that. But But this should work. I guess the one thing we need to worry about here is we're using the X and Y registers. So we need to make sure that when we return from our interrupt handler, we put those X and Y registers back the way we found them. So what we could do here is when we enter the interrupt handler, we can, well, we can't push X and Y onto the stack directly, but we can push the A register. So we can push A, and we can transfer X to A, push A again, so this is pushing X, transfer Y to A, and push A again. So here we're pushing A, here we're pushing X, here we're pushing Y, and so when we return, we need to do that in the reverse order. So we need to transfer A to Y. So we're going to pull A, transfer that into Y. So we're essentially pulling Y off the stack. Pull A, transfer A to X. So now we're pulling X off the stack. And then finally just pull A off the stack to put the A register back the way we found it. So we need to do this stuff to make sure that the X and Y registers are back the way we found them so that we can use them here. And also the A register, because we need to use the A register in order to do this stack operation. So with all of that done, that should give us some, sort of hacky software debouncing. So let's go ahead and assemble that again. I'll write that program to the EEPROM again. Now let's put the EEPROM back in, reset here. And I don't know if you can tell, I can definitely tell it's very slow. It feels kind of laggy almost because it's sitting in that loop in the interrupt handler. So when I push the button, yeah, it's a noticeable delay from when I push the button to when it increments, and that's because it's in that loop in that interrupt handler, waiting for any switch bounce or whatever to subside. And the display is not going to update, even though it increments the counter immediately. The display won't update because we're just inside that loop in the interrupt handler. So we have to get out of the interrupt before anything else can happen. So that's why this is maybe not the best solution, but it might be good enough. Certainly if we trim those timers down a bit, I made them pretty long, but we could probably find a happy medium if we trim that down a little bit so that it feels responsive. And if we're not doing anything else with the processor, maybe it's fine. So one thing I didn't mention was, if we look back at what we're doing in the program here, the interrupt is getting triggered. We're pushing a bunch of stuff on the stack. We're incrementing our counter. We're sitting in this delay for a little while. And then we're clearing the interrupt by reading from port A. And then we put everything back on the stack and return from the interrupt. But what I'm not mentioning is this interrupt flag register. So remember, this interrupt flag register, we could read this and it would tell us which thing caused the interrupt. So in our case, it would be the CA1 bit would be set. And also the IRQ bit would be set to tell us that something had triggered an interrupt. But I'm not actually reading this in the interrupt handler. And that's because in this case, I really don't need to. I set up my interrupt enable register to just trigger an interrupt on that one bit, that CA1 bit. So I know that if I get an interrupt, the only thing that could cause it is CA1. So I don't really need to read the interrupt flag register to figure out what caused the interrupt because there's only one thing that could cause it. But in a more complex system, we might need to do that. So a couple of scenarios. One scenario would be if we have multiple 6522s, we could have many inputs coming in and other things going on. And instead of having a single connection like we do here going into the interrupt request line, we could have these ANDed together in some way so that the single interrupt request for the processor could be triggered by any of a number of these 6522 chips. And in that case, we'd need to read the interrupt flag register from each of them to figure out which one caused the interrupt. And that's where this IRQ bit at the top is very useful because you can actually do that bit compare operator that I talked about, and that'll load this top bit into one of the processor flags. And so you very quickly figure out where the interrupt came from. But even in this case where we have a single chip, the interrupt still could be caused by multiple sources. In our case, we know it's not because we only have one thing enabled that'll cause it. But, if we had some timers set up or some other things, then we would need to read this interrupt flag register to figure out what actually triggered the particular interrupt that we're handling. And perhaps in a future video, I can talk more about how these timers work to show a more concrete example of that. But hopefully this gives you a sense of how the 6522 chip here can be used to have an interrupt coming in and forward that interrupt to the processor in a way that the processor can then service it when it gets a chance to run its interrupt service routine and then clear that interrupt. and also, show a little bit about how we can use a delay loop to do a little bit of debouncing. But again, you might want to do that in hardware so it's not quite as laggy, or you might want to update the timer to be a little bit tighter. There's a bunch of things you could do to try to improve on this. You might also want to, if you're doing this project at home, you might want to try adding several buttons, and not just hooking them up through the CA1 bit, but also hooking them individually up to individual inputs here. And then you could, perhaps diode OR them together into so they all trigger the interrupt. But anyway, hopefully this gives you some ideas of where to go from here. Because remember, if you do want to try any of this at home, you can get more information on parts and kits and everything over at my website, eater.net/6502. And of course, as always, I want to thank all my patrons who help support these videos and help make these videos possible. So as always, thank you.